Okay, I can start now. All right, thanks. Okay, good afternoon. Let's start by reviewing the topic that we discussed in the last lecture. And we concentrated on this topic about what happens in the saturation region of the IV characteristics, and particularly a phenomenon known as channel length modulation. As VD increases, the length of this pinch-off region or the velocity saturation region increases. Right? So we developed a model which started by analyzing the electrical potential profile, and we found that the channel length or the length of the depletion region is a function of VD minus VD set. Specifically, it's equal to L prime, hyperbolic sine or arcsinch of VD minus VD set over E set times L prime. And the main thing is that delta L is proportional to L prime, whereas L prime is the characteristic length of the exponential rise or fall of the electric field or potential. In other words, electric field starts in the drain. At the drain edge is very strong and decreases exponentially. That exponential decay has a characteristic length called L prime, and it's equal to 3 Tox xj. The smaller this characteristic length is, the smaller the pinch-off region would be. So the main thing that one can do to reduce the channel length modulation effect is to reduce L prime through reduction of Tox and xj. It's okay? That's the main conclusion. All right, let's see. And we also, from there developed this concept of output conductance. Output conductance is defined as 1 over source drain conductance, and source drain conductance is defined as dID dVd. All right, these notations are good to know. And the general behavior of the output resistance as function of VDS is that it starts fairly low in the so-called linear region, start to rise where the channel length modulation becomes, well, first of all, start to rise as we enter the saturation regime of the IV characteristics. And the slope decreases rapidly, meaning our out increases rapidly as VD increases beyond VD set. Our out, theoretically, is a linear function of VDS. Eventually, channel length modulation is no longer the mechanism that determines output resistance. Something else takes over, and we identified that mechanism as drain-induced barrier lowering. As VDS increases, VT drops, therefore current rises. Right? And eventually, this is the part you don't always see, depending on the design of the transistor and the range of the VD operation. But we could see a regime where hot electron effect becomes important, and our out will start to drop. All right? And ID set as function of VD can be written down in expression from the channel length modulation theory. In one approximate form, one can show that output resistance is a linear function VD minus VT. And another mechanism that determines the output resistance is Dibble. And finally, impact ionization. Okay? Any questions about what we talked about last time? Yes? No? All right. Now, before I start today's topic, I just use half of the slide to sort of take one extra step from where we ended, and to kind of derive a useful result, which we will then put aside, and we will not use until a few lectures later. And that has to do with the maximum electric field That's in the channel length. And before I derive that result, let me just tell you what that is important for. The maximum electric field in the channel, which of course is just the peak field in the pinch-off region, which, using the assumption we use, occurs right at the edge of the drain. Is that right? Because electric field keeps increasing as we move from the beginning point of pinch-off region toward the drain. The electric field keeps increasing, right? Exponentially, and reaches its peak at the edge of the drain. Now, this peak electric field is very important because it's this maximum field that basically determines things like impact ionization rate and hot electron reliability. The reason is all these hot electron phenomena are very strong functions of the electric field. So it's really that maximum electric field that determines everything that has to do with breakdown, with substrate current. So we want to get a model for electric field, and we can get there very easily based on what we already have. All right? Let's see, how do we derive that? Okay, I'll just give you the, okay, seems that we are not getting, all right, that's fine. I'll give you a simple derivation today, and maybe in the future we'll go back to the equations derived last hour and get a more exact verification for you. But so today let's do this in a semi-quantitative way. The thing to remember is that electric potential increases exponentially with y prime. You remember y prime equal to 0 is the beginning of the pinch-off region. Is that right? So from there, it increases exponentially. It increases actually according to hyperbolic sign, but today, for simplicity, let's just say it increases exponentially with the characteristic length L prime. Is that okay? Next, because of that, electric field also increases exponentially. If you just differentiate the field, you get, differentiate the potential, you get the field, right? Electric field increases exponentially from the beginning pinch-off region with the characteristic length L prime. So if you plot the electric field, it kind of increases exponentially like this. Again, using approximation, let's say, I don't know. Let's say this is where L prime is. Y prime equal to 0 is here, let's suppose. All right? At that point, electric field actually is not very large. It's equal to the field for velocity saturation, maybe 3 times 10 to the 4th volt per centimeter. Excuse me, it's not large electric field. From that point on, it increases. Now, the area under this curve, of course, is equal to the voltage between the drain and the beginning of the pinch-off point. Namely, the area is equal to VD minus VD set. Do you agree? Right? Should be equal to VD minus the voltage drop across pinch-off region. But mathematically, do you know that this area under exponential curve is always equal to EM times L prime, EM being the maximum? All right? You may or may not know this result. But the fact is that the area under exponential curve is equal to the value of that exponential function multiplied by L prime. All right? You can show that very easily. You just integrate something, integrate this, let's say, from I don't know what to say, integrate from this, right? Or any function from y prime equal to 0 to y prime equal to, let's say, k. You know what you're going to get? You're going to get L prime exponential k over L prime. You know, exponential k over L prime is just the value of that function at the limit of integration in times y. Okay? It's very easy to understand that. The area under exponential curve is always equal to the peak value times a length. And length is just that characteristic length. Every exponential function has this characteristic. Okay? So I'm just using this fact here. I'm not deriving anything for you. So if you actually carry out this integration, you get EM times L prime. But earlier we said that area should also be equal to VD minus VD set. So you put these two together, you get EM equal to VD minus VD set over L prime. Now, that's a very simple and very useful result. Later on, if we wanted to know what the electric field is in the channel, we know it's equal to VD minus VD set over L prime. All right? It's as if VD minus VD set is the voltage drop over this high field region, over this pinch-off region, this velocity saturation region, and as if L prime is the effective length of this high field region. Okay? You see what I'm saying? All right. Now, in reality, I want you to be careful. Don't really take that statement literally. Is the pinch-off region length exactly equal to L prime? No, it's several times L prime. We just derived that last lecture, right? It's proportional to L prime, but not equal to L prime. Okay? All right? But the maximum field, I'm not talking about average field, I'm talking about the maximum field in that pinch-off region is equal to VD minus VD set over L prime. Is that right? Okay? Do you understand that? All right. So as far as its maximum electric field equation is concerned, you kind of can think of L prime as the effective length of that high field region. All right? But this doesn't mean that the high field region is equal to L prime, is equal to several times L prime. But the peak value is equal to VD minus VD set divided by L prime. All right? So we have this result now. We'll put this aside, and we'll use this later on. Okay, any questions about this analysis of the pinch-off region? Yes?
This is valid only in the pinch-off region, right?
That's correct.
So we have V of y in that equation.
Go on.
Is that better? I mean, is it better to use V of y prime to?
V of y prime, I mean like this. We had the equation yesterday. Is that what you're saying?
For the entire channel length.
Oh, no, it's not. Let's just agree. This equation is only good for the pinch-off region. This is what we derived last hour, except we wrote down in a hyperbolic sign. Today I'm using a simpler form. So no, definitely this is only good for the pinch-off region. All right? But fortunately, we also needed only to use it for pinch-off region for today's purpose, for EM. We only need to integrate it through the pinch-off region. You see, we're equating this to VD minus VD set, not equating the whole thing to VDS, right? VDS will be equal to electric field integrated throughout the channel. But we only want to integrate the field in the pinch-off region and equate that ED. Yes, Jane, you have a question?
Yes, probably you can compare this, because we have two feature size like this L prime, and previously we have the L, which is for the dipole.
Aha.
Then could you compare this?
Make some comment about those two quantities. We used to, so far we have seen two characteristic lengths, by the way. There won't be a third one, all right? So that's good news. That's it, all right? For the dipole case, we had something, we got something called L, which is equal to 3 times Tox times X depletion. And for this depletion region called the CM channel length modulation, let's call this, all right? So marginal analysis, we had L prime, which is equal to 3 times Tox times xj. Let me first emphasize the similarity. The similarity is that mathematically they came from very similar analysis. We're solving some kind of quasi-2D Poisson's equation using Gauss' law, set of Poisson's equation, yes? And they both represent some characteristic length of the rise of the electric field or voltage or potential, right, in that exponential or hyperbolic sign, cosine manner. So that's the similarity, all right? What's the difference? The difference is that, you know, for one case, for the dipole case, we have to look for a Gauss box, which is more or less flat from all the way from source to drain, right? And at this boundary, there's no vertical field. So when we consider all the possible choices, we decided XD max is the best. Certainly, you understand if we choose the edge of the depletion region, there's no normal field, right? The normal field is 0, satisfied. And also, more or less, is constant from source and drain. More or less. It's not a good choice. We're not happy with it, but reasonable. Is that right? Because in reality, it might look something like that. the boundary of the depletion region. Is that right? But if you look at all the way from source to drain, it's not a bad choice. It's okay? Now, for the second case, for the channel length modulation, we're not looking for a boundary that's flat from source to drain. We're only looking for a boundary that's flat, in this a few hundred angstrom region near the drain. In that case, we could still try to use this, but that's probably not a good choice. Is there a better choice? So we argue there's a better choice. Just use the channel length, junction depths. The reason is that the junction depths, we know there are many electric field lines because the corner is is sharp, right? One of these field lines probably pretty flat in this a few hundred angstrom distance. And that field line can be used as the bottom boundary of the Gauss box. You see what I'm saying? Right? Okay. So probably Jing has in mind the following question. That seems to be easy for me to justify this or justify that. How would one know, or did anyone really know the first time he or she look at this, which is a better approximation? Well, let me admit to you, it's not, okay? It's not so easy. We don't know. So this is why there's research. Not everything is simple as homework. I guess what is research is probably means solve a problem. It's a little harder than homework, meaning that maybe not 1 hour. You may have to spend 20 hours on it, right? It will be too much of a homework. But that turns into a research project. And when you have that much time, you will be able to try 2 different boundary conditions, compare these two approximations with some available data, with some 2D simulation. With that, then you come back to think, well, can I really think that this is a better approximation than the other one? And hopefully you will agree that it is a better approximation. So it's not an easy choice to make. It's not something that's obvious that clearly the other choice is wrong. But that's why textbooks and lectures tends to be able to cover a lot of ground in a short time, because we're only telling you what works. We're not telling you what the other paths have been tried. It didn't work, right? So does that help? Is that the question? All right. Okay. All right. And in reality, I just want to remind you, even with Dibble case, we've shown you that actually experimentally we did find that, it has to do with TOX. It also has to do with XJ and has to do with X depletion. Is that right? So empirically, we know that it has something to do with that. We'll put a 1/3 power here. Right? You remember that? Okay. We have to start somewhere as an analytical approximation, and you can also always try to refine it afterwards. Okay. Any other questions? All right. Now we're going to start a new topic today, and the section is 5.5. The topic is compact SPICE MOSFET model, and I'm trying to follow the order of the textbook. So the textbook bring us to this topic here. But I think I will deviate from the textbook coverage quite a bit. Instead of talking in general about the MOSFET model, I just concentrate on one MOSFET model specifically. It's called the BSM3, all right? And this is because I happen to know a lot about that. This is also a topic that Kevin is very familiar with. Also, Jing Shi is the expert on this. You have questions, you have good help here. And it's a result of the research of many students over the years at Berkeley. It's the most popular model for circuit design used today. So we're going to concentrate on that. But first, I have 1 or 2 slides, maybe 1 slide to introduce what is a compact model, what's meant by a SPICE model. In case you don't know, SPICE really is a circuit simulator, all right? It's a circuit simulator. So when a circuit designer designs circuits, he or she uses the simulator as the tool. He will put in a transistor there, put a capacitor between this transistor, that transistor, so on and so forth, and then ask the simulator to simulate the behavior of the circuit, right? And based on that, the designer will judge whether the circuit meets the the spec of the circuit to go. If it doesn't, he'll think about some way to change the circuit, add another transistor here or something like that, and simulate again to see if it works. If it doesn't work, he will make another try. So he goes through this many times until he finds a circuit that will meet the performance requirement, and that's the end of circuit design, right? Okay, so that is the purpose of a circuit simulator, and SPICE happened to be, how should I say, the pioneer circuit simulator. It was also developed at Berkeley by Professor Rohrer and Professor Peterson and their students, and so very often, that style of circuit simulation is called SPICE simulation, even though the code is really not what the Berkeley SPICE codes are, or may not even look like it, may be quite different, but this type of simulator engines are called SPICE simulators, okay? Sometimes. And certainly they are called SPICE simulations, that kind of simulation. Now, in order for the simulator to work, the simulator has to have a way of representing the transistor behavior, right? And you can see if you really want to represent a transistor very accurately, you have to put in a lot of physics. So that's something, not really in the domain of a person who designed a simulator, more in the expertise domain of a person who knows a lot about transistor physics. Right? So these models then are put into the SPICE engine or work with SPICE engines for circuit simulation. Do you see what I mean by that? All right. Okay. Now, another thing I will say, so this is called a compact model because there are other ways of representing the transistors, such as solving electron hole diffusion and drift. And that's not a very practical way of simulating circuit, not practical at all. Whereas compact model will represent the transistor behavior by a very long analytical equation. It's very long. If you print it out, it probably will be 20 pages long, this equation. All right? But it is a compact model by the standard of computer simulation. Right? So we're going to talk about the compact model. Now, compact MOSFET model plays a very unique role in the semiconductor technology because it's a unique link between two very large worlds in the semiconductor industry. One world is circuit design, CAD, circuit design, and CAD, right? That's one part. You probably know a lot about those. And another part of the semiconductor industry is technology development and manufacturing. It's also very important. Both sides, a lot of investment, lots of people working on both sides. And yet, if you ask, what's the information exchange between the two? What does the circuit designer get from all this technology development from the manufacturing world? Not that much. Basically, it's the design rule and the compact model. That's what it is. So compact model is supposed to really capture everything that's in this technology manufacturing, give to the design. All right? At least ideally, that's the function it performs. Maybe it's not doing it perfectly yet. But ideally, that's what the compact model will do, right? Because that's the link that's between this. That's all. You know what I mean? All right. Now, so the effort of technology development and impact of manufacturing statistical variation gets translated into the product performance through the compact model. So you don't capture that accurately, then the product would not take maximum benefit of the capability of the technology. If the model is too aggressive, then the manufactured silicon chip will not be able to meet what the simulator tells the designer that the design could meet. So that's the reason we need an accurate compact model. All right? Now, this BSIM stands for Berkeley Short Channel ICFET Model, BSIM. All right? Now, BSIM 3 is right now widely used. BSIM 4 was released about a year ago, and over time probably will overtake BSIM 3, and has been chosen as the first industry standard model for circuit simulation, and it's chosen and supported by an organization called Compact Model Council. under EIA, and it's a consortium of about 20 companies, and so they have selected BSEM as the standard model. And what makes BSEM special is that it incorporates a lot of models of device physics, such as inversion layer quantization, and a lot of things that you have heard already in this course. So today, as we review this model, hopefully you'll find a lot of familiar things what went into that. The reason that this good physics makes the model good is because, of course, physics makes the model accurate. It makes it scalable. Now, what does that mean? Well, let me start one thing at a time. All right, we'll do this. Scalable means this. In fact, even accurate, I think I can report to you what that really says is this. Years ago, compact model is very much dependent on curve fitting in the following sense. A person would take some model from the textbook, right? Probably fairly simple models. And today, by the standard of this course, we'll consider them not accurate. But you take a model like that. Accurate or not, we're just putting many parameters. Doesn't matter if parameters, really corresponds to the mobility of measured mobility or not. We'll consider everything as fitting parameters. Then we'll compare this model with measured IV curve and then try to adjust the parameters until they fit, right? Doesn't matter whether, the mobility is real mobility or this resistance real resistance or not. We'll just do that. To some extent, you can do it. The problem is that if you want this model to actually predict all the dependencies on VG, VD, body, and the channel length, it's very difficult. People find out it's not possible. So as a result, very often, people will make these a so-called a binning model. That is, they would use one model to represent transistors with channel lengths between, say, 1 micron and 2 micron. They use a different model to represent transistors with channel lengths between 1 micron and 0.8 micron. A third model represents transistor channel lengths in 0.8 micron, 0.6, so on and so forth. Do you see what I mean? In other words, if you curve fit one transistor, maybe you can, but you just cannot capture the variation of the characteristics as transistor size start to change. All right? But with a good model, it should be scalable. That's what that really means. Basically means scale with L, right? So it captures the effect of L. Turns out that's a big thing because no model before BSEM was able to do that. So BSEM was the first model that could do this. Capture L dependence to be simple. That's really what it is, all right? Okay. Scalable is a big word. And turns out accurate function of all the VG and VD is not easy either. Later I'll show you what that means. Maybe we'll have some example that you will see it's not easy. And to be really fancy then, a good physical model could even be predictive. I mean, if it's really this good, then we should be able to predict, what happens if the oxide is just a little thinner than you originally planned, right? Right? Just change the oxide thickness model should be able to do it for you. A curve fitting model won't do it for you. But BSEM would do it because, BSEM, it captures the effect of oxide thickness in many things, not just in the, say, the C-ox that determines the IV, the current. Everyone thought about that. But by now, T-ox affects many things, right? Short channel effect, channel length modulation, right? And many things. So if you really capture those, then it can be truly predictive. And it's good for statistical modeling. Predictive means it can predict what happens when oxide is deliberately made thinner. Statistical modeling meaning, in the variation, we have this somewhat random variation of oxide thickness. Is that right? From lot to lot, day to day, right? And how are you going to model that change in SPICE? In SPICE model. But if we just measure the variation of statistical variation of oxide thickness, plug that into BSEM, because BSEM then immediately translate that into its impact on the various aspects of the transistor. That certainly will make this a good model for statistical modeling. You see the point, right? How can you use kind of curve fitting to do that? How many, statistical devices are going to fit? And and how do you use them mathematically? So that's the question. Another thing I want to just call your attention to is parameter extraction. Parameter extraction just means determining those parameters that are used for quote-unquote curve fitting. All right? You can try to model all this dependence accurately by putting in a lot of fitting parameters into the model, because the more fitting parameters, the more you can adjust the model to fit the details of the data. Well, people have found out just by adding in a lot of fitting parameters, because that's needed in order to get a chance of fitting, parameter extraction becomes very difficult, because these parameters, as you throw them in at random, turns out if you change this, let's say let's say a particular device characteristics depends on 10 different parameters. So as you change one parameter to change one device characteristic, it also affected other device characteristics. Can you see that possibility? Whereas if you really model this model physically, of course, then that's no problem. You change the parameter, even TOC, suppose you use that as fitting parameter. No problem. You choose it to try to match the current. It happens to also match the other things fine. You know what I mean, right? So actually, even the parameter extraction has become easier. Used to be a company think they're going to need months to characterize a model, meaning take months to determine the model parameter for BSEM model, for not BSEM, for SPICE model. But today, their companies claim they can do this in minutes. So that is the kind of difference that it could make. All right. So BSEM 4, BSEM 3, what kind of physics are included in the model? The single way is a little bit of review of the things we have talked about. So the short narrow channel effect, short channel, narrow channel effect, right? Also short channel as well as narrow channel. Do you recall what they are about? Short channel and narrow channel, right? Okay. Both the normal short channel and the reverse short channel, these have to be included, right? The non-uniform vertical doping and lateral doping effects, right? Non-uniform lateral doping is believed to be responsible for the reverse short channel effect, for example, right? The mobility reduction due to vertical field, is that right? Okay. Just think about that. If you don't know the physics, how would you think about how to describe the mobility? Remember what the universal mobility model did. It consolidated so many different variations into one thing that you can deal with, right? VT, VG, oxide thickness. If you didn't know that, how are you going to model this? As function of body bias, as function of VT, how do you do that? Huh? Carrier velocity saturation effects, channel length modulation, substrate current induced body effect, we haven't talked about that. Quantum mechanical effective gate oxide thickness model, we talked a little bit about that, right? Earlier part of the course. Gate dielectric tunneling current, now we haven't quite talked about that. We'll talk about that later on. Gate induced drain current, GIDO, you remember that, right? Now RF model, we haven't talked about that. I think next lecture I want to say something about that, because as you know, RF is a very important topic for wireless applications. Unified flicker noise model. Do you remember flicker noise? Yeah, we talk about that, right? Not in detail, but you have read some reference, right? You know at least the genesis of it. We haven't talked about thermal noise. We'll just say a little bit next hour about thermal noise as part of the RF discussion, right? And asymptotic layout-dependent parasitic model, we haven't said much about it, except we mentioned series resistance. And it turns out resistance, capacitance, these are all very important parasitic models. Now, the good thing about having a physics-based model is improve the model accuracy and ease the parameter extraction. You can use one set of parameters to model a device over a wide range of L and W. That's called scalability. You can predict effects of process variation on device characteristics. That's good for statistical modeling of manufacturing variation, right? And you can even try to extrapolate existing technology to future generations of device. Kevin, for example, has a small part of research. He's able to actually give designers models for 0.1 micron device today. Everyone can download that from the website so that the designers can do their circuit design. You don't have to wait for transistor silicon to be made. And if you are a designer, you know how frustrating that is and how difficult it is to have some SPICE model to do circuit research for future technology. But we believe that you can actually make pretty good prediction what it's going to be, right? Because it's no longer a curve fitting exercise, right? Okay, so those are what the things that one can do. And okay, all right. So specifically, if you look at the equation used in Beeson, how does Beeson describe VT? You start with a quantity called VT0. That will be the basic model, VT model, maybe for long channel transistor, you know, simple model. This is something that Beeson will not be able to predict because it depends on doping profile, doping density. So this will be what we will call a fitting parameter. All right? Right? We'll have to determine that, right, from measurements. Yes, right? Okay. And then, let's see, what do you think the first term is describing? What it's trying to do? What's that called? Body effect, right? Is that right? Do you remember body effect has this? Now, using this way to describe body effect, what's the implicit assumption about a doping concentration? Uniform. So do you actually think this is the very best way to model it? May not be, right? Okay? So take a look at this equation here. What do you see there? Linear. And it's also a body effect. Now, does this ring a bell to you? Why should VT be a linear function of body bias? Okay, that's good. And so that will be appropriate for a device with retrograde technology. Is that right? And what about somewhere in between? Well, maybe we'll have some K2, some K1. You know, that's your hope that we'll model. Is that right? So you get a sense of how compact model try to cover a lot of things. And even though there's no way for us to anticipate any detail in the doping concentration. Is that right? At least we hope we'll get there. Okay? I can give you a hint, you know. A lot of people thought, even today, I believe, they would think this is just a empirical thing because, you know, one would see that threshold voltage is, you know, sometimes a fairly linear function of VB. But actually, you know, the students have thought about this many years ago, and they realize why the transistor should behave this way. And so that's why it's in the model, all right? Now let's see the third term. Any idea what that's about? Okay, now this is an example where it's really, there's not much, how should I put it, not much physics in things like this. You can always try to justify it, but there's some limit you can do about it. We're trying to model some narrow width effect. Now you notice in the narrow width effect, I did not introduce some quantitative model to you, right? For one reason is that it's very difficult to pin down what the edge of the isolation is like, because it's very much dependent on the technology. Every generation is different. It's very difficult. And so in that case, you know, one would just resort to some very simple qualitative observation. If you do something like that, 1 over W plus W naught seem to fit the observed behavior. So that's what it is, right? Whether it's a normal or abnormal narrow width effect can be determined by the sign of case 3, right? You know what I mean? Okay? And if someday someone derive a you know, more physical model for narrow width effect, you can imagine we'll be very interested in putting that into Beeson model, right? So there's always more room for improvement. Okay? All right. So I'm not going to analyze every equation in this detail for you. As I said, the equation will be, you know, 10 pages long. But it's just one equation I'll go through it so that you get a sense what it's about. Okay? Now this equation has to do with the reverse short channel effect. Okay, pocket implant type of a device. And again, I did not introduce to you any quantitative model. Turns out there is a more quantitative model. It's much more complicated. This one, you know, people still think users still feel it's working well, so we're not bothering with it. But actually, I believe in one of your readers, paper in your reader, a paper by Bing Yu, who is now working for AMD, he actually published a paper deriving a more physical model for pocket doped transistors reverse short channel effect. One equation would describe both the rise and fall of that VT as function of channel length. All right. And finally, this delta VTH is a term that captures the short channel effect. So that's the equation we derived together in this course for the Dibble effect. That's exponential function of L, for example, and it's function of Tox, and a lot of things come into this equation. Okay? All right, next slide probably reminds you what that is about. Do you remember we say the VT roll-off is a function of channel length, and that function channel length is here. Remember, it's a sum of two exponential terms. Is that right? Okay? I actually use both terms. I suggest you just think about one term for day-to-day thinking, remember? But the computer can handle two exponential terms without too much difficulty, so actually use both of them to get better accuracy. And this is for BSEM3. For BSEM4, we actually went back to hyperbolic sine function of L, because that's where the original derivation was that. We thought that expanding this into series of exponential functions make it easier for engineers to use the model. But turns out in extreme cases, for example, if a channel length is very short, actually does not work that well. Going back to hyperbolic sine function actually works better. So going back to that. All right? But the VD dependence, do you remember the VD dependence? Right? The linear dependence between channel lengths, between a threshold voltage and VD, is that right? And also there's a term in front of that. Do you remember those? Okay. So these are actually put into that. And finally, what determines this characteristic length? Do you remember? Has to do with oxide thickness, depletion region thickness. Is that right? Now, what happens here? Well, we know that depletion. We know that this quantity itself is just approximation, and given that this is a compact model, there's nothing wrong to give the user some choice, some additional parameters that he can or she can adjust to fit this data even better. You see, if you don't have any fitting parameter, then it's very difficult to fit all the results. Is that right? First of all, I should say that's why this is here. You see, so you would think if everything is right, this quantity should be just 1. Remember, that's what we derived in this course, in this class, right? But suppose 1.2 makes this VT dependence on L much better. Why don't we allow that? We should accept that when we derive this model, this is approximation. We don't know how good it is, right? Let's scrap that. Right? And also, we know that the VBS dependence is not very well captured by this X depletion. Because after all, the depletion region is not even flat. Is that right? So empirically, it appears by adding this with this as fitting parameter, one can fit the result better. So that's how this model gets come about. You start with a core physical model that you feel pretty good about, and then you have to make some compromises and allow the user some flexibility to get to the kind of accuracy that really a circuit designer wants. These days, people want the SPICE prediction to be within 5% of what they get in the silicon. And in fact, even that every year is adding. They really want to be, 2% accuracy. So everything you have to model very accurately. All right. Okay. The next step is we start with the concept of channel charge. All right. Instead of directly looking at current, we start with the concept of charge of the channel. In the charge of the thinking about a charge in the channel, in the strong inversion regime, when VG is much larger than VT, we know that the channel charge is equal to Cox times VG minus VT, right? That's easy. When the channel is is in the sub-threshold regime. We also have an expression to describe this channel charge. You should find this fairly familiar. For example, the charge in the channel subthreshold regime is exponential function of Vg, remember? In fact, it's Vg minus Vt, all right? But not just over the thermal voltage, but also this ratio, n, right? N is always larger than 1. Our model would say it's 1 plus Cox divided by C depletion. Is that right? Yes? But as a SPICE model, do you really want to use the C depletion here? Again, thinking about the geometry, we don't even quite know how deep that depletion region is, right? Should we just use long channel approximation depletion width? Doesn't matter. Doesn't make sense, right? So why don't we just see what data tells us this n should be? You know what I mean? Is that right? Okay. And let me just tell you what this office, well, maybe I won't, maybe I will, okay. This line would have predicted, this equation would have predicted, let me do it this way, all right. The data, log of ID versus VG, you probably recall, trace out a curve like this. Is that right? That would be the data. Is that right? We often say it's a straight line from VT. So suppose this is VT. If we take that literally, this would be what we are saying. Do you follow what I'm talking about? This would literally be what we're talking about. In reality, it's not like that because this is approximation. We omitted this range. Is that right? So one thing we can do is we think we could add this with a V off term. That's one way to think about that. You see what I'm saying? All right? And of course, this constant in front, actually, if you review the approximation of the charge sheet model earlier in this course, we actually did derive something like that. You see what I'm saying? All right? But a full charge sheet model will involve iterative solution. Right? So we don't want that. Let's first start with this two piecewise model. In the strong inversion, we have this equation. In the weak inversion, we have that equation. Is that right? Okay. Now we try to make this smooth and single piece by looking for an equation that actually reduces to these two expressions. I'm sorry. Excuse me. In the extreme case of subthreshold and strong inversion. And in between, it's just a smooth function. And so students tried several functions, and they chose this one. Now, I won't go through this with you. Take my words for it. If you take this equation, that channel charge is simply equal to Cox times VG ST effective. VG ST effective, think of it as if it's equal to VG minus VT. It's not. Okay. And this is the expression for VG ST effective. Take my words for it. This function becomes Vg minus Vt in the strong inversion region, all right? Inversion. If you just take the assumption Vg minus Vt is much larger than the thermal voltage, you will find this whole thing reduces to Vg minus Vt. And if you take the opposite assumption that Vg minus Vt is several thermal voltages smaller than 0, in other words, Vg is less than Vt by more than a few thermal voltage, this expression reduced to the first expression in the previous slide. Okay? Take my words for it. Now, question.
When these smoothing functions are selected, are they fit to things like GM?
This is what they are fit to. All right? So this is how we decided this is a good function. It said we tried a couple. Not that there are that many functions one can think of, but there are certainly more than one. Now, again, this is no news to you. As I said, I want to use this opportunity to tie some things together, see how this thing put together. You remember we talked about how you can measure the capacitance between the channel and the gate. Is that right? The channel charge, right? Not the overlap thing. We just look at the channel charge, not the body charge, for example, right? By looking at the current flowing between the capacitor current flowing between the gate and the source with the source string shorted, all right? And the channel charge is supplied by the source, Therefore, if you measure the current flowing into the source, you're actually getting the channel charge. All right? It's very easy to deal with the overlap capacitance. I'll remind you in a minute. You end up with this curve. That this is the capacitance versus VG. You don't see any capacitance until you get a threshold voltage, right? Or close to threshold voltage. And it rises gradually. There's no assumption about suddenly you get inversion charge. Just gradually rises until you eventually saturate a Cox. So this is giving you the channel charge, the Q inversion, dVG. That's what this data is telling you. Is that right? Now, how did we manage to get rid of the overlap capacitance? It's very simple. It has to do with this coordinate. This vertical coordinate, we'll put a 0 here. The raw data actually would have the 0 somewhere here. In other words, this thing is going to saturate to a constant. Because once you get into depletion, right, then the only capacitance you see is between the gate and the source and drain is the overlap now. Is that right? In a strong inversion, what you see the entire channel. Yes? Yes? In the depletion or the accumulation region, the capacitance between the gate and the source drain is only the overlap capacitance. Do you see what I'm saying? So what eventually you see, that little value is the overlap capacitance. So you just set your 0 at this point, then you know your real channel capacitance. Is it okay? Because this capacitance that we call CGDS, all right? CGD/S, CGD/S. This capacitance is equal to TQ inversion TVG. Therefore, Q inversion is simply equal to this quantity integrated by with respect to VG. All right? So it's this integration will give us the charge. Yes? So if you do that, you will be able to plot out Q inversion as function of VG. Without an assumption, this is just data. And this is the log scale. I want you to pay attention to this log scale. So both in the strong inversion region, as well as the subthreshold region, as well as the region in between, the transition. Do you see what I'm talking about? All right? There's no theory here, just experimental data. Is it okay? Yes? Yeah? And you do see that this charge is exponential function of VG, as we expected, right? In the subthreshold region, yes? And eventually become logarithmic or linear function VG as we expected. And in between is in between. There's no theory, just data here, right? So what we can do then, to answer your question, is to compare a smoothing function to this data to see if it works. All right? And next slide will show you the kind of a fit you will get. All right? So that's that function. That's called the VGST effective function that gives us a channel charge. Now it's now plotted against the data. The line is the model, and measured data is the line, and the data is in the stats. Okay? So it looks pretty good. Certainly, you will always want to change certain things like oxide thickness. Here we have several oxide thickness, 50 angstrom, 70 angstrom, right? And you change the doping concentration, 6E17. I don't remember what that is, all the way to E18s, right? And of course, we also change the body bias and all those sort of things, right? That's how you test this. Yes.
But when you pick a quantity like comparing this against just Q inversion, ultimately we're interested in first some sort of ID, and more specifically, you'd think with a smoothing function, we would be into some small signal quantity like the gradient of the current.
So I will show you that. Of course, eventually we'll test this against things like GM. In fact, something even stronger than GM. But just to comment on why we start with charge rather than starting with current, even though we know finally what we want is current. You know, if you go directly to what you finally want, then you fall into this trap of curve fitting, right? You don't know whether you really got it right or wrong, because after all, you can fit that current by changing your mobility or changing your charge. Is that right? So you always want to ask, what is the first thing that I can fit that really doesn't have ifs and buts? So get that right, And then I go to the next thing. In the case of charge, there's no ifs and buts. You can measure charge from capacitance. Has anything to do with mobility, for example? So you want to model that first. You take that as given, put into the current, and then figure out what the mobility should be, right? Hopefully mobility is what you really think it should be as the universal mobility. If it's not, then you may be, you may want to think more, see what else you're missing, right? Okay. It turns out in this case we didn't have to think more. It does fit the current as you would expect. For example, what would have not fit, even if you got a charge right, if you got the mobility right, what else would make it not fit? If you didn't consider loss saturation, still won't fit, right? So you do this step by step, and you do that right. So next step indeed is mobility, right? You know the charge, and you have to know the mobility. So again, I can tell you, BSIM 3 did not have this universal mobility in it. In other words, we did not mobility, something like mu naught, a constant divided by 1 plus this quantity Vg plus Vt over 6 ox to some power, 0.6 power or something like that, right? Some k power. We didn't use this equation because at the time we found that maybe too unnecessary for the circuit designer, because after all, circuit designer up to that point was used to model mobility just a function, some linear function of Vg minus Vt, right? Or Vg minus Vt square kind of thing. So what we did was change that to Vg plus Vt for BSIM 3. All right. But in BSIM 4, we actually introduced this because it does appear that approach was paying off. That is adding more physics. So BSIM 4 add even more physics, putting through this real universal mobility. All right. So BSIM 3 already made a mobility function Vg plus Vt, which caused a lot of confusions among users because they have never seen anything that's a function Vg plus Vt, right? Everything's function Vg minus Vt, but you know why that's the case. So this is the mobility model we have seen. So, but what BSIM 3 had, by the way, is actually just still power law functions of Vg plus Vt, not minus Vt. It says plus 2 Vt. This is because VGST effective, I mentioned to you, in strong inversion case, reduces to what? Reduces to VGS minus VTH, right? So minus VTH plus 2 VTH is VGST plus VTH. Okay, so that's how it looks. Now we're ready to talk about the linear regime of the IV characteristics. Does this look familiar to you? Does this equation look familiar to you? I hope it does, right? For example, what is this thing doing here? What is a bulk doing here? What is it doing here? It has to do with that what we call M. Is that right? Yes. Okay. Let me. Maybe you didn't quite. Okay. Let's not go through all the details. What you probably remembered is W, mu, Cox, no problem, right? What do you remember? You remember Vg minus Vt, then what? M, Vds over 2 times Vds. Is that right? Okay, let's do this exercise, all right? Multiply this VGST into this equation here. Would you do that for me? What you get is VGST effective, right? And again, remember, what is VGST effective equal to in strong inversion? Is VGS minus VT. Is that right? So you have VGS minus VT. We got it here now from this 1. Is that correct? So now VGST effective multiply into here. Okay? What do you get? You're going to get this, right? Okay? Now, let's not worry about this. There's some details here. Let's not look into this. We can even justify this actually took care of the diffusion current in the transition region. But let's not worry about that. Because I'm sorry, I don't really mean this. Did I do this right? VGST minus VGST. Okay, I think I made a mistake here. I think this is lowercase VT. Is that right? I don't know if Jean can help me. Does it make sense, Jean? Does it make sense? What's that? Is that thermal voltage? It really should be plus 2 VT. Okay? I don't know either, all right? We'll have to go back, look at it. Today, let's ignore this, all right? If you ignore that, then VGST cancels out. You get your VDS over 2 term, is that right? And this A bulk is what? Is that M term, okay? Yeah, please. Yeah.
I mean, it can't really be the real VT.
Yeah, I guess it's not.
Right.
It's probably thermal voltage. What I seem to remember is the thermal voltage. I remember this justification. It actually took care of the diffusion current, make the model even better near the transition. All right? Okay. So because it's small, today for our purpose, well, in strong inversion, we can ignore that, right? Well, we are above VT. But we are not way above VT. We found out adding this thermal voltage actually makes this model better. All right? There's some justification for doing that. So this is what you want. Finally, we didn't look at this. Do you remember this part? Remember this part? Okay? All right. Hope you remember. Okay? All right. Good. And then this is without RDS. If we had RDS, we model like this. Again, we have gone through this. Okay? It's not too difficult. Right? All right. Next, we need to find up to what voltage the equation in the previous slide is okay, is good. Now remember this piecewise model, we follow that equation up to VD set. Is that right? Yes? Beyond that, we don't follow it. Okay? So we follow up to VD set. Now, VD set is equal to this. Does this look familiar? It's okay? All right, good. And so I will not get into the details here. Remember, when we derive this, we don't have the M here. I was saying, you could try to find where the M should go in or should not go in, right? And so let's not worry about that, but let's just point out things that will look familiar to you, like this ESAT term, right? Okay. Now that's for without series resistance. With series resistance, the derivation is much more complicated. All right, this is just mathematics, of course, but this could still be done, but it has to be presented in this polynomial formula, right? But it's not much physics in it, so we certainly won't ask you to think about that. Okay. Next, talk about the R-out model. R-out model, actually, it's this model was, you could say, was derived for the Beeson model in that up to that point, I think the only model in the literature is to explain this by channel length modulation. And actually, the student that worked on the first version of Beeson model developed this R-out model. And that's Jianhui Huang. And so what we noticed by comparing with the data is that this RL doesn't fit the expected behavior of channel length modulation. It's for that reason now we interpret this as having to do with channel length modulation, having to do with Dibble, and then having to do with substrate current impact ionization. All right? And there were several equations that's included in Beeson in order to model that. So there are 3 mechanisms: channel length modulation mechanism, and you can probably imagine the kind of equation used there, even though I did not put it on the slide, but we just saw those equations in the last lecture, right? And drain-induced barrier lowering. Well, you will be asked to derive one such equation in the new homework that Kevin just assigned to you. Is that right? So you will see how this can be done. And the substrate current induced output conductance, we will not be able to deal with that until later on in the course. All right? Okay. Now, when you put all those terms together, this is what BSM3 plot out would look like. The solid lines are the data. The dots are the lines is simulation. The dots are data. Okay? The lines are simulation, BSM plot, and the dots are the data. What do we mean by data? You take transistors, and first of all, the students actually made these transistors in Corey Hall on the 5th floor in the micro lab, right? And he would vary the oxide thickness, and he would vary some doping concentration, and certainly when doing the measurement, there will be different channel lengths to use and different VG. One can different channel lengths here on the left-hand side, right? Different channel lengths is available, right? And he will vary VD. Of course, he would also vary VG. But in one plot, you cannot show everything. So here we just show you the two things is usually you don't see. That is showing you the changing in channel lengths rather than showing you the change effect of VG, right? So this is several different transistors, right? And you notice that the model agree with the data very well for different channel lengths. This is known as scalability. Scalability, all right? You see what I'm saying? Okay, so one set of parameters, you can model the effect of changing channel lengths and the effect of changing drain source voltage. And even more surprising is can even model the changing effect of changing oxide thickness. Is that right? Okay, let's see if we can understand the physics here. You notice this curve cross each other several times. For example, let's just concentrate on two curves. One is for the thick oxide, right, the triangle. This 156 angstroms, the triangle. You notice triangle started with very large R out, then gave us smallest R out, then give us the largest R out again, all right? Let's not worry about this part. We haven't talked about the impedantization yet. Just look at this two parts and compare the thick oxide transistor and the thin oxide transistor, which start with very small R out and end up with a very large R out. Just compare these two cases, 55 angstrom, 155 angstrom. All right? So the question to you is, would you have expected this? Or having seen this, how would you explain it? Why does the thin oxide transistor start out with a smaller R out? Let's just think about that. Why does it have, please speak into the microphone, please.
I think for the thin oxide, the Dibble effect will be more tremendous than the thick oxide.
All right, so you're commenting on the Dibble effect. So you say for thin oxide, Dibble effect is stronger or weaker?
For thick, it's weaker.
For thin oxide, Dibble...
For thin is stronger.
I'm sorry. For thin oxide, you think Dibble phenomena is stronger, huh? Okay. For thin oxide has the effect of suppressing Dibble. And if we don't like Dibble effect is something we don't like, first of all, let's remember. Okay, Dibble effect is something we don't like. It's a bad thing. We want to suppress it. One very effective way to suppress this bad thing, this VT roll-off, this Dibble effect, is to make thin oxide, make the oxide thin. Remember that conclusion? All right. So thin oxide will suppress Dibble effect. So in a thin oxide device, the Dibble effect is weaker. It's weaker. All right, your comment.
Well, I actually have a question if you can explain it. Is that VGST that's VGS minus VT0 or minus the VT associated with the channel length?
Called minus VT associated with channel length. All right. Okay. All right. Back to this discussion here. It's a very interesting comment that in the thin oxide, by the way, it's correct. The Dibble factors into this. All right, let's think through this then. What does thin oxide do to the Dibble effect? Let's agree that thin oxide suppresses Dibble effect. If suppress Dibble effect, if we suppress, how would that affect R out? When Dibble effect is taken away or reduced, does R out rise or fall? Joe, what do you think?
The R out would increase.
R out would increase. The IV curve become flatter. That means R out increase. And that's exactly what you see, right? Thin oxide has largest R out here, right? Smaller R out. Is that right? Yes? Okay, next. Why does the thin oxide have a lower R out in this region? In this low VDS region, please.
So in triode, the thinner oxide will cause more carriers to show up in inversion.
Exactly. Think about ID versus VD curve. You have a thick oxide transistor. You have a thin oxide transistor. I'm exaggerating. I'm sorry. Doesn't the thin oxide give you a larger current? This is 55 angstrom. This is 156 angstrom. Isn't thin oxide expected to give you more current? More current meaning larger slope. Larger slope meaning smaller R out, right? R out is nothing but inverse of the slope. That's all we're seeing here, nothing special. Okay. Finally, I'm saving what's really related to channel length modulation for the last. Does this confirm or contradict what you expect the effect the thin oxide has on channel length modulation? Does this data confirm or contradict that? What do you expect how do you tell which device has stronger channel length modulation based on this? A device that has very small channel length modulation would have very large RL, right? Right? Remember the slope having to do with channel length modulation. Remember that? It's a linear function of VD, linear function VD, right? You do notice there's a regime where it's fairly linear, right? It's pretty good. Do you agree? Is that right? Okay. And the larger slope is meaning what? Meaning the R out is rising faster, meaning it's getting saturated faster. Is that right? That means there's less channel length modulation. When this curve becomes very flat, it means no channel length modulation. Is that right? If there's a large amount of channel length modulation, that means it took forever for this curve to really saturate. That means this thing will rise really slowly. That means a lot of channel length modulation. Is that correct? So thin oxide has very little channel length modulation. Thick oxide has more channel length modulation. Does that make sense? Makes sense, right? So if you really want to be quantitative about it, if you're curious, you're going to try to compare the slope to see if quantitatively agree with that L prime dependence on the oxide thickness, right? If you're really curious about it. You know what I mean? Okay? All right. Now this has a sort of a surprising effect. This plot has a surprising interpretation. Suppose you extrapolate this to 0, right? To 0 R out. Extrapolate linear point to 0 R out. What do you expect it to be? What do you expect it to be? What do you expect to be? This quantity. What is it? VD set is excellent answer. Do you remember? This R out is proportional VD minus VD set. Remember that? Okay. So again, you know, I did tell you I wasn't quite sure that derivation approximation made was right for that R out. But then when you see data like this, probably the approximation is okay, right? Probably okay. Too much of a coincidence. Of course, you're going to compare this with the IV curve to see if it makes sense or not. All right? And if it makes sense, then you have to agree it's probably right. If it doesn't make sense, you'll say that derivation is probably not right. Okay? Maybe the approximation was too aggressive. We can do something better. So to some extent, this right now may be the best way to experimentally determine VD set. Do you know what I mean? Because experimentally, there's no way to define VD set. You get an IV curve, where do you point and call it VD set? You see what I mean? You measure IV curve, ID versus VD. You can measure as many such curves as you want. How do you define VD set? Yes? You know that? So experimentally, it's very difficult to determine VD set. This may be the best way to do it, because this you only require experimental data. You extrapolate that linear region to 0, what you get is VD set, right? I'm not trying to say this is a very useful thing, but this is kind of an interesting argument. That is, suppose you need to determine VD set experimentally, how would you ever going to get it, that number? Right? Yes? Perhaps. Experimental is always a problem. Where do you travel? You hope you can see a region where it's pretty straight line. This is going to be problematic, all right? But just because it's for fun, let me just show you this. I'll let you do it. You know, on the left-hand side, there are several different channel lengths. Well, you can see whether for different channel lengths, VD set is varying in the range you agree or you expect it, which means you have to have some opinion. How should VD set vary with channel lengths, right? You have to have an opinion about that first. And then you can see if the left-hand side agree with your opinion. All right? Okay, so those are the kind of things you think about when you see data. Once you have data, a lot of things came about. That's why experiment is very important. You can talk about theory, but eventually we have to build these theories on experimental data. All right? Okay. So then we are ready to talk about IV curve. Okay? That's the last thing you want to talk about. And so that you know you're not just fitting curves. And so here's the IDVD, IDVG, IDVD. So this is the kind of thing you see. Okay? And here's an interesting plot. And this turns out was data that given to us by AMD. Early I show you some transistor made by students themselves. Now here is some data from the industry. This is experimental devices where the engineer just asked the fab to change the oxide thickness between 2.5 nanometer, 3.6 nanometer, 4.7 nanometer, and 5.7 nanometer. It's a fairly simple experiment, right? As a result of that, VT is different now for all 4 devices. Is that right? Okay? So we just take the BSIM parameter, don't change anything, just change the TOX and VT to this measured value. And then you see the IV curve fits pretty well. Okay? It didn't fit this impedantization part that carefully. That's because that part of the model wasn't. Well, we started by using this was the I think the benchmark starting point. We started using this data. This was only available data to get all the other parameters. And in this, there was no information about impedantization, of course. So there's no way to get that data accurately. So it's understandable it doesn't fit that part very well. But overall, you can see this is the meaning of predictivity, I would say. It's a predictive model, you have to admit. It's not just the curve fitting. Once we know these basic parameters, then you can predict what change of the device design will have on the transistor characteristics. Okay? There's a question. Yes? Sorry. Okay? All right. Now, let's just check 1 or 2 others. We can do this very fast. Now, remember, we have all this model so far still has a problem. That is, we still kind of implicitly assume the surface, the charge is at the surface. Therefore, TOX determines a lot of things, oxide thickness. But if we accept the fact that electrons are not right at the surface, but at some T inversion, or what we call the DC, or let's say T inversion below the interface, isn't it kind of makes sense that this is our effective oxide thickness? Is that right? Kind of makes sense, doesn't it? All the capacitance and maybe even current should depend on this, not the physical oxide thickness, right? And what makes this really interesting is that this is saying the effective dielectric thickness is not a constant, but a strong function, maybe not so strong, a function of Vg. Why? Because this inversion layer thickness, or centroid, is function of Vg plus Vth. Remember that? Remember that? Following what I'm saying? All right? This is a VGST effective, okay? Plus a Vg. Remember? So this also is put into BSIM 3 first for the CV, and also in BSIM 4 for the IV, okay? So now you can see the CV model matches the data very well. Before that, even the data actually is like this, okay? The transitions are too sharp. This is what kind of data you will get if you take the, the chapter 3 kind of model, you will get this kind of thing. And this result is quantum effect. See that? Okay? And this decrease of the capacitance is due to the poly depletion. All right? Is okay? All right. So there's several curves here, right? For example, this very sharp transition here, that's the piecewise curve that we usually learn in the undergraduate textbook, right? This is, accumulation, inversion, and threshold. Depletion and inversion. By the way, this model is still used in circuit simulation today. People still use this. All right. The next model is a slightly advanced version that actually try to capture this Poisson equation solution and give you this, but did not consider the quantum effect. And finally, quantum effect will give you this. It's okay? All right? All right. Okay, and so this in BSEM4, this is quantum effect also put into the transistor IV characteristics. So when we say, you know, ID is proportional to Cox, it's really non-effective Cox now, and which is proportional to 1 over Tox plus that TDC inversion, we call it XDC, all right? The DC inversion charge centroid, okay? And that itself is a function of VG, okay? Also a function of threshold voltage and a function of oxide thickness. So this, we think, is going to be make a real difference in the accuracy when the oxide thickness is comparable, or not comparable, maybe not that much larger, the inversion thickness. Is that right? Okay. So that's the last slide of today's lecture. We'll end here. Any quick questions about today's discussion? All right. So next lecture, I can tell you what we're going to do. We're going to add a few more things that the textbook will not cover. We kind of tag this on at the end of the SPICE model discussion because it is first introduced into BSEM and then published in physics journals like IEDM conferences like that. So I certainly consider that as part of the BSEM research, but it's really interesting device physics in its own right, so we'll use next hour for topics like that. Okay.